would be, we are now recording. Okay, so inductive reasoning. All right, so inductive reasoning is characterized by drawing a general, so this is one of the key words to this, a general conclusion from repeated observations of specific examples. The conclusion may or may not be true. All right, so inductive reasoning, characterized by drawing a general conclusion from repeated observations of specific examples. The conclusion may or may not be true. Sometimes we will interchange the word conclusion when we're talking about inductive reasoning with the word conjecture. And conjecture in itself means an educated guess. So an example, simple example of inductive reasoning. It's rained for the last 4 days, therefore tomorrow it's going to rain. You're just, again, looking at a series of repeated observations that it has rained for the last 4 days and drawing the conclusion that it's going to rain the next day. Give me a second. Sorry, I got a cat on a rampage. All right. Now, some other things about inductive reasoning. If we are reasoning inductively, it cannot prove its conclusion true. Cannot. Right? At best, it just shows it's probably true. That's the best we can do. Right? So at best, it shows it is probably true. So it can be analyzed in terms of its strength. All right, so, and kind of just a way to kind of remember, because we're going to look at another type of reasoning. And so to differentiate those two in a simple way, we look at, we're drawing a general conclusion from repeated observations of specific examples. So those specific examples in terms of when we talk about logic, we refer to them as premises. And that is what we're using to draw our conclusion. So we are generalizing from more specific premises. Okay. All right. So inductive reasoning. All right. Can I go ahead and turn the page? We're going to have that written down. So I'm going to go ahead and flip the page. And talk about deductive reasoning. All right. So deductive reasoning is characterized by applying general principles to specific examples. All right, so I like to phrase this as I'm applying generally held rules, laws, facts to draw a conclusion. So, you know, instead of looking at it as rain for the last 4 days, therefore it's going to rain tomorrow, which we reasoning inductively, I am looking at, you know, looking at the barometric pressure and sort of atmospheric scientific things to draw a conclusion that it is going to rain. Next day, looking at radar. Hold on a second. Wow. My cat is just absolutely just got the zoomies. So hopefully it just doesn't jump on the computer while we're working. All right. And where we were looking at inductive reasoning was kind of looking at specific examples to apply to a general conclusion. This is kind of the opposite. So inductive reasoning, again, I'm looking at going from specific to general. Deductive, kind of general to specific. It's just kind of a short way to remember the difference of the two. But so for a little bit more about deductive reasoning, whereas inductive reasoning can only be analyzed in terms of like its strength, how much does it convince you, but it can never actually prove its conclusion. Deductive reasoning, we can prove the conclusion, though that conclusion may be absolutely false. But the logical flow would actually prove it. Now, what we mean is there's two components looking at a deductive reasoning type argument. One of them is validity, and the other is soundness. So these are two ways we analyze a deductive argument. So it's validity. So an argument is valid if its conclusion, no apostrophe, if its conclusion follows necessarily from its premises. Now, so again, a deductive, you may reason something out, looking at a deductive argument, and the conclusion follows from its premises, but the conclusion itself may be blatantly false if the premises themselves weren't true. So logically, your premises will lead you to that conclusion, but the conclusion itself may be completely bogus just simply because your premises themselves were not true. So that takes us to soundness. An argument is sound if it is valid. So if an argument is not valid, that is, its conclusion does not follow from its premises, then it can't be sound. So to be sound, first you have to be valid. So an argument is sound if it is valid and its premises are true. And so I'm looking at a type of deductive, simple deductive argument. This is an age-old one. So premises. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. That would be a type of deductive argument. So in mathematics, as we build a mathematical system, and we're writing conditional statements, theorems that then have to be proven, those are deductive arguments. Now, I may use inductive reasoning to draw a conclusion that something may work, but then I have to formalize it and actually write a deductive proof to actually say, okay, this is now completely proven. So, and then I would throw one other thing in here. The book doesn't mention this, but what I call simply intuition. Or sometimes we characterize that as a gut feeling. So there is no basis. There is no, I can point to, okay, I've looked at a series of examples and then draw conclusions. So it's not even inductive and it's not deductive. It's just, I just have a feeling this is what should be. And in mathematics, intuition is actually very important. I mean, that's how we can start down, a path of actually discovering something. Just because I got a gut feeling, this is how it should operate. All right, so there are, go through a few of the kind of homework problems. The first 10 or so deal with inductive and deductive reasoning. So let's look at a couple of examples. Excuse me. All right, so just number one. Number one. The next number in the pattern. So I'm going to write all that, but here's the pattern. And 24, 26, 28, 30, 32. Okay, so the problem actually states the next number in this pattern is 34. That seems reasonable. But what it's asking really is determine whether this is deductive or inductive. And since you are looking at just a series of observations, that is the sequence of numbers, 24, 26, 28, 30, 32, appear to be increasing by 2 for each term, then it's reasonable to conclude that this is 34. Now, it may not be, probably is, but the reasoning itself would be inductive, since I'm looking at a series of observations, specific observations that each term increases by 2. All right, so when you look at, you're going to get 4 choices on the answers. 2 of them are deductive, 2 of them are inductive. And then from there, they actually mix up the definitions. So on the one selection says the reasoning is inductive because a specific example is being used to reach a general conclusion. But remember, that is the definition of deductive. So the correct choice is the reasoning is inductive because a general conclusion is being made from repeated observations of specific examples. Let's find one that's deductive. So I'm just now looking at number 2. Now, number 2 says to find the perimeter P of a square with side length S, I can use the formula P equals 4S. So the perimeter of a square with 7 inches is 4 times 7 equals 28 inches. In this case, number 2, so find the perimeter of the square. To find the perimeter of the square, kind of shorthanding this used formula. Perimeter equals 4 times S, where S is the side length of the square. And so if S equals 7 inches, your perimeter would be 4 times 7 or 20 inches. But here I'm looking at what general principle of perimeter formula for a square and applying this to a specific example, in this case, a square with 7 inches. So this would be an example of deductive reasoning. Questions thus far? All right. So in the first 10, it looks like the first 9 problems deal with just inductive and deductive reasoning. Deciphering between the two, looking at just having to decide whether you're looking at an example of deductive or inductive. Now from there, it's really just a bunch of number patterns, looking at pattern recognition. And that's going to be a big focus for the next couple of weeks. And so they start fairly simple. They're not so, looking at now number 10, it's not asking to determine whether it's inductive or deductive reasoning. It's just saying what is the next most probable number in a sequence of terms. I got 7, 10, 13, 16, 19. So it wants to know what the next most probable term would be. And so looking at, since it looks to be increasing by 3 each time, I would say 22. There's going to be several like that. So figure those shouldn't be too difficult. I'm looking at numbers, so this was number 10. This is going to be number 16. Here we go. There's 2, 5, 10, 17, 26, 37, and then wants the next most probable term. This there. So all right. So see if you guys come up with that one. What is the next one? Just chat it in. Type in chat. What do you think is the next term in this sequence? Oh, somebody be brave. Chat it in. Or just verbally say it. Yeah, I've got somebody. Yep. That is correct. So it is 50. And the deal is here, if I can see it increases by 3 and then increases by 5. And then I would add 7, and then I would add 9, and then I add 11. So I'm going to conclude that I'm going to add what? 13. The next term after that, I would add 15. So it'd be 65. All right, so. Pretty much. Okay. So come back and look at that one. All right. Looking at the last problem, I'm going to help you. I like this one. The last problem, honestly, to me, it's not too difficult because they give a big old hint. So I'm going to have you guys think about this one without the hint. All right. So here is a numbered sequence of numbers. And so you got to come up with the next number in this list, the next most probable number. So two things. One, let's just go with first, what do you think the next number is? And go ahead and chat that in. All right. And you are correct. That is the most probable number. I will agree. It is 1. And if you had to get, now it doesn't ask this, but we're going to ask it. What would be the next number you think after that one? Somebody else chat that. What do you think? What would be the next most probable number? Yep. So both of you are correct. That actually will be the next number. All right. It is 4. And so I would probably conclude if I'll do this one, the next one seems to be what, 1, and the next one after that would seem to be what, 5, and so on and so forth. However, here's the big question. Why? And without the hint, this one's tough at first. And what makes this one tough is that starts out with 12, and then there are 3 consecutive ones. Then it appears to be alternating 2, 1, 3, 1, 4, 1, 5, probably 1, 6, 1, 7, 1, etc. Anyone have any ideas as to why? Right now we are reasoning inductively. And so now we're trying to actually build a deductive argument. Does anyone have a guess? Have a thought? All right, I'm gonna help you out a little bit. See if so I'm gonna give you a little bit of a hint. We have one of these on campus. It actually is in the big grassy courtyard area out front of the school. What is out front in that big grassy area? All right, somebody's. Yep. Now, not just any kind of, so yeah, we have a big clock. It has what's called a Westminster chime. So some of you may have a clock, typically grandfather clocks have this. But when we say Westminster chime, when the clock strikes on the hour, how many times does it chime on the hour? Very quiet out there. All right, so let's see here. So, so if it's 3 o'clock, it's going to chime 3 times. But, oops, there we go. How many times does it chime on the half hour? How many times does it chat on the half hour? Typical grandfather clock. So it's 12:30. How many times does that clock chime? That's it. All right. Thank you. Once. So it's going to chime that number of times on the hour, whatever that hour is. If it's 5 o'clock, it's going to chime 5 times, but on the half hour, chimes once. So putting this in that context, now it makes perfect sense. 12 o'clock, it chimes 12 times. 12:30, it's only going to chime once. 1 o'clock chimes once. 1:30, it's still going to chime 1 time. 2 o'clock chimes twice. 2:30 once. 3 o'clock 3 times, so on and so forth. So then the 111 makes perfect sense once we put the context of what is building that particular sequence of numbers. All right. So one other thing in this particular section, and I honestly, because I've got 2 121s this semester, and it seemed to me one class I was able to do this, and one I was not on the very first day. So refresh my memory if you've seen this problem. This one, if you have seen it from me, it was on the very first day of class. All right, so what I'm looking at is the sum of numbers, counting numbers starting at 1, going from 1 to 100. Do you remember me putting this problem up on the board and talking about the little 6-year-old boy who was sitting in an elementary classroom, and his teacher gave the students this problem, thinking it would keep them occupied and busy for a while she graded papers or whatever it was she needed to do. And that this little 6-year-old boy, about 30 seconds later, gave her the sum. Does this ring bells? Did we talk about this problem on the first day of class? Yay or nay? Okay, let's see. Okay, fair enough. I thought you were the ones I did not show the problem to. So let's talk about this problem. And normally what I do if is I throw the problem up there and then I let everybody in class work on it for a while. And it's kind of humbling when you stop to think that a 6-year-old was able to come up with the answer, which is, incidentally, 5,050. Excuse me. But was able to do it in like 30 seconds. And so after I let everyone work on it for a few minutes, I will go on to say, don't feel bad that you were outgunned by a 6-year-old. That particular 6-year-old later on in life, and to this day, and incidentally, this 6-year-old lived back in the late 18th century, so a very long time ago. So there were no calculators. And he became known and is still referred to this day as the world's greatest mathematician that ever lived. He was a prodigy. His last name was Gauss, Carl Friedrich Gauss. Not an area of mathematics that he didn't influence or do some work in. So question is, how did he do it? How was he able to come up with that sum so quick? So what he did, a one attack method to the problem and to solve the problem was just start at 1 and go 1 plus 2 is 3 and 3 plus 3 is 6 and 4 plus 6 is 10 and 5 plus 10 is 15 and just keep adding until you finally get to adding all 100 of them together. It's going to take you a while, but yeah, you would get there. But what he recognized, again, no way I would have done this at 6 years old, was addition is commutative. I can add in any order I want, still get the same thing. So instead of just going directly 1 plus 2 plus 3 plus 4 down the line, he went, what is 1 plus 100? Well, that's 101. That is, he added the first and last term of the sum. And then he went, what's 2 plus 99? Well, that's also 101. And what is 3 plus 98? 101. And 4 plus 97. And now, so using some inductive reasoning, I would conclude if I keep doing this, I'm going to keep getting sums of 101 all the way down the line. And then, well, if there's I'm adding up 100 things, then there are 50 pairs. And what is multiplication but repeated addition? So if I can just go 101 times 50, that would have to be the sum. And it turns out, of course, 101 times 50 is 5,050. So, yeah, no way at 6 years old I would have been able to figure that one out. Maybe no way on the multiplication. So, quite confident I couldn't have done that. But there's going to be about 3 or 4 problems. One of them you're going to have to modify a little bit, dealing with, excuse me, dealing with adding in this kind of fashion. Now, he went on later, about 20 years of age, and came up with a formula that we're going to look at next time. That you can just plug in the number of terms you're adding starting at 1 into this formula, and that will be the sum no matter how many numbers that you have added up. And I'm going to go ahead and write that down. So again, about 20 years of age, he figured out that if I add up to n, so any starting at 1 and adding up consecutive natural numbers up to a number n, that if I plug into this formula, that will be the sum. Now n, incidentally, it's called the ordinal number. And what n is and will be. So next class, we're going to look at 3 summing formulas. There's oodles and oodles and oodles of summing formulas. This is just the first one we're looking at. We're going to look at 2 others in addition to this one on Thursday, as well as some other things about sequences. But n is the number, the actual number of numbers or things being added up. And that will be important to know or remember when we're looking at some of these other summing formulas. So if I'm just adding up consecutive counting numbers, then this last number will be the number of things I've added up. So looking at how it would apply to this, adding up all the numbers from 1 to 100, then n is 100. And if I plugged in to that formula, 2 goes into 100 50 times. And 100 plus 1 is what? 101. And of course, we already know 50 times 101 is 5,050. Okay. And I believe that's pretty much everything. Yep, in that section that I want to do. So, today is the 14th. So I'm assigning 1.1, setting due date on the 16th. Past due date as always. And it is now assigned. So, and so when you go in your assignments page, I believe this one's going to appear before the geometry ones. So you're looking for 1.1, homework section 1.1. So your assignment, there's maybe 3 of you still have to take the geometry test for the first time. So try to have that done and wrapped up by Thursday for sure. And do this work in 1.1. On Thursday, so we're gonna get a little bit more technical with summing formulas and looking at different types of number sequences, specifically like 2 types for sure: geometric and arithmetic. Some formulas associated with each. A way to find the next term of a sequence called method of successive differences. And again, summing formulas. I don't think we'll get to the figure of numbers, which are, but we might, which are also number sequences. So expect a full day for sure on Thursday. Any questions? So if there's no questions, again, if you still need to take that first exam, try to get that done for the first time before Thursday, or any other outstanding work you have in geometry. And definitely everybody, regardless, make sure you do 1.1. And so otherwise, be safe out there. And I'm always being cautionary, but I have some, again, because my wife works at the hospital, I kind of know what's going on there, and it's rough at the hospital right now. So I don't know how else to put it. So just be safe. All right. So be cautious out there. So that said, I will see you on Thursday. Everyone have a good day.